Okay, so in this lecture, we will look at something called Parseval's theorem, right, which is a way of, um, you know, working out a quantity based on all the coefficients, right? So we have seen that how if you have a function, a periodic function, which can be written as a Fourier series, you get a whole bunch of coefficients, right? So there is a convenient number that you can form by collecting all these coefficients, which is related to a very nice form of the function. And this has some very beautiful applications, one of which we'll also look at in this lecture. Okay, so there are these two equivalent ways of expanding a function of period 2 pi, right? One is in terms of cosines and sines, and the other in terms of exponentials, right? So we know how to do this. And so now let's look at what happens to this function f of x, right? It's a periodic function. So if you want to consider the average of the square of this function, right? So, we have seen how, electrical engineers are often interested in the average value of the square of certain functions, right? So like AC current, for example, right? It's helpful to measure the average of the square. So if you measure the average of f of x squared over a period, then it's given by, you can check this. So what would happen is, so the left hand side is just integral minus pi to pi f of x the whole square dx 1 over 2 pi, right? Since you're that's the total interval. Now the right hand side, I'm just giving you the answer, but you can check this explicitly. So what happens is, you have these, every term, you take a product of this entire sum with itself. Now, so it's going to give you all these terms which are, squares of itself, right? That is one term that you get, but you also get these cross terms, right? So we have seen that it's profitable to think of this as an expansion of a vector in an orthonormal basis, right? That's what a Fourier series really is, right? So if you take the square and then you integrate in a period, so that's basically like taking the inner product of these different basis vectors with each other. So we have seen that they're orthonormal or orthogonal for sure, right? Normalization you have to work out. So, and we have left it open, but basically any two distinct basis vectors, their inner product is 0. So therefore none of these cross terms will contribute when you do this integral, and half a naught the whole squared will just give you half a naught squared when you average over a period. And then we have seen that cosine squared and x, right? So the average of cosine squared or the average of sine squared, both of them are just half. So therefore you will get half summation over n a n squared and another half summation over n b n squared, right? So again we can show that the average of f of x squared, if you're working it out in terms of the other coefficients of pertaining to the exponentials, then so in general these Cn's are complex numbers, right, as we have seen. So here you will get mod of Cn squared, right? So this is also something you can explicitly verify by, first of all arguing that the cross terms, the integrals pertaining to the cross terms will vanish, and the integrals involving just the diagonal terms, you can show that it's exactly this quantity. It's going to give you mod Cn squared summed over all n going all the way from minus infinity to plus infinity. So this relation is called Parseval's theorem, or the completeness relation, right? So it's called completeness because there is this hint of these basis vectors which form a complete set, they form a basis. So there is this completeness which is satisfied by all these cosines and sines, or all the exponentials, right? Even if one of them is missing, it's not going to be possible for you to expand every vector in the space in terms of all these exponentials, if even one of them is missing, right? So each of these basis vectors is an essential ingredient, right? The coefficient along each of these. And so in fact that's what allows it to be called as a basis, right? So it's a very compact set in the sense that each of them brings in a certain amount of information which the others are not able to give on their own, and also there is no redundancy, right? So everybody is valuable, and there is and everybody is essential, and there is no no unnecessary members in the set. So that's why we have seen that for finite dimensional spaces, all bases had exactly the same number of elements. So here it's an infinite dimensional space, so the number of elements in your basis is infinite, but cosines and sines are they form together they form a basis, meaning that there is no redundancy here, right? So when it comes to finding the size of the basis, one may have to be careful, but the point here is that all the cosines are essential. It's not even if one of them is missing, you will not be able to expand an arbitrary vector, arbitrary function in terms of a series like this if even one of these frequencies is missing. Every one of them is key, right? So that's the reason behind the name completeness relation for this theorem. Let's look at a beautiful application of the Parseval's theorem. So let's consider this example: f of x equal to x from minus pi to plus pi with period 2 pi. We have this, and write it as a complex exponential series. So we want to work out these coefficients Cn such that f of x is this infinite series. So C not immediately we can check that it is just 0, because it's going to be just the average of this function, right? It's going to go to 0 evidently. So and when n is not equal to 0, to find Cn we must do 1 over 2 pi integral minus pi to pi x times e to the minus I n x dx. So we can do this by parts. So you have u dv, which is uv minus v du. So you can convince yourself that this second integral is just 0, right? Because it's the integral of cosine and sine in an interval which is an integral multiple of the period. So it doesn't matter what n is, this integral is going to vanish. And then if you work out the algebra carefully, you will see that this will give you I over n times minus 1 to the n, right? So if n is negative, then because you have n sitting here in the denominator, you're going to have one more negative sign, right? So on the one hand you get this minus 1 to the n, which oscillates signs when you have even and odd n, but also if your n itself is negative, that will give you another sign, right? So there are these two kinds of signs you have to be careful with. So if I work this out carefully, the series expansion for f of x is I times minus I to the ix minus e to the ix minus e to the minus ix divided by 1 plus e to the I2x minus e to the minus I2x divided by 2 minus e to the I3x minus e to the minus I3x divided by 3, so on, right? So you can see immediately that these are all, it's going to have only sinusoidals, no cosines are allowed in this expansion, right? That's because this is an odd function, right? So it's more convenient to work with these complex exponentials when for the application of Parseval's relation, right? So that's why I've written it like this. Now if we bring in Parseval's relation, right? So we have to find the integral of f of x squared dx, and divide by 2 pi in the interval minus pi to pi. So f of x is the same as x, whereas x squared dx, the summation is equal to summation over all n from minus infinity to plus infinity except n equal to 0, right? So we see that we have I over n. So mod of in times minus 1 to the n, mod of this Cn squared is going to be just 1 over n squared, right? I doesn't contribute, mod of I squared will just become 1, minus 1 put to the power n to the whole squared again will just become 1. And yeah, of course we have to omit n equal to 0. We have seen that C0 is equal to 0 separately, we have seen that. So this is the same as saying 2 times summation over n, going from 1 to infinity, only the positive values of n allowed, 1 over n squared, right? There is symmetry in this. So what we have is the result that 2 times summation over 1 over n squared is pi squared over 3, or in fact what we have found is the value of the Riemann zeta function at s equal to 2, right? So you might be familiar with the Riemann zeta function, which is defined as summation over n going from 1 to infinity of 1 over n to the s, right? So s is the variable, but if you put s equal to 2, then that's the Riemann zeta function at, that's what we have here, and we have managed to show that this is equal to pi squared by 6. So this is a very beautiful result. So in the 21st century, perhaps it's not something that is certainly it's not unknown, or it's not something which is unfamiliar. A lot of people are aware of this result, but it carries a certain magic value, even by 21st century standards, right? And it was first discovered and advertised by Leonhard Euler in 1735, right? So he used other methods. So there are plenty of different ways of obtaining this, right? So we have managed to get this using Parseval's relation within Fourier series analysis. So there are many independent ways of doing this, some which are more elementary, there are others, but this is a beautiful result, right? So we have already seen another series, the Leibniz series result, which was also sort of like a magic trick which got us there. And in fact, there's a whole bunch of these kind of series which one can extract using Parseval's relation, or other methods, Dirichlet conditions. So these are all things which we can play. We can in fact come up with our own functions, which periodic functions, and look at what happens with Parseval's relation. Or we can use this as a way to try and find our own series, and then these are probably most likely going to be series that are already known, which we can verify. Okay, so on that note, that's all for this lecture. Thank you.